So for this short lecture, I'm going to talk about the method of manufactured solutions. These are particularly useful because as we get to 2D and 3D problems, such as your Project 2 assignment with a plate with a hole in it, exact solutions can be hard to come by. And so if we want to do a convergence test, the first step in the method of manufactured solutions is to first just create a solution, just arbitrarily make one up. Now it's important that we choose a solution that's not contained within the approximation function space. That means that we don't want to pick a function that's going to be represented by the shape functions exactly, because then we wouldn't see any convergence. So in this case, we'll take something relatively simple. We'll say that t star, so t star means that this is our chosen solution. So we're saying the answer to the problem that we're going to solve is the square root of x squared plus y squared. And so now the question is well, what's the problem that's the answer to? And it turns out that's a lot easier to determine than it is to pick a problem and then try to find a solution to it. And so once we've chosen the solution, we'll calculate the heat flux from that solution. So that just involves taking its gradient and multiplying it by the thermal conductivity. So we have the derivative of t star, or the gradient of t star. To do that easily, there's a couple things that we need to do. So first we'll just say that, well, the square root of x squared plus y squared, we'll define that as r, just the radial distance from the origin, and dr dx, if you carry that through, you're going to get that it's equal to x over r. Relatively simple to show. Dr dy would just be y over r, so that's simple enough. And so that makes it easy to compute the gradient. So the gradient of the temperature field is minus k times x over r in the I direction, minus k times y over r in the j direction. And so now that we have the flux, we're going to plug the flux into the strong form and solve for the heat source. So in this, we're going to take the divergence of our flux, which of course is coming from our chosen exact solution, subtract from that s, which at this point is yet unknown. So we're going to solve for s that makes our temperature field a solution to the heat transfer equation. And now we're going to need to take derivatives that look like ddx of 1 over r. So this is just to do this in advance, so it's simple when we do it later on. So ddx of 1 over r is going to be negative 1 over r squared times x over r, and that simplifies to minus x over r cubed. Ddx or ddy of 1 over r would just be minus y over r cubed. And so now we can compute the flux, or the divergence of the flux. So it's going to be, it's a product. Well, it's x divided by r. And so if we take the derivative of x, we get just 1 over r minus, then we're going to take the derivative of 1 over r. So it's going to be x squared divided by r cubed. Likewise, the derivative of the y component of the flux with respect to y is going to be 1 over r minus y squared over r cubed. And then that still minus s is equal to 0. We factored out the k. And so simplifying this and solving for s, what we're going to get is that in the end, s is equal to minus k over r. Okay? And so now the next step is to just solve this problem, to which we now know the answer, using your code with the geometry of our problem. And so if the geometry of the problem is a plate with a hole in it, well, we know the problem, we know the heat flux solution, we know the source term, but what are the boundary conditions? So the simplest thing we could do is just specify on the entire boundary. Now the entire boundary includes the boundary of the hole. So on the entire boundary, so we'll just say gamma t is equal to gamma, so it's just the whole boundary. We're just going to specify that the temperature is equal to T star. Okay, now that's fine. The only problem with that is that in your code, you have some code that computes the heat flux. And if you do a convergence test where you set the entire boundary to be prescribed temperature, then you don't actually test to see whether or not your heat flux computation is correct. So what we can do instead is apply different boundary conditions. So on the boundary, on the outer boundary, let's say, we're going to specify the temperature, so that's gamma t. But now on the hole, we're going to specify that the heat flux is going to be specified. And so these are written as T is equal to T star on gamma T, and Q is equal to Q star dot N on gamma Q. Now the Q star dot N is because the flux is a vector, but in terms of the boundary condition, it's the amount of heat entering per unit area on that surface. So if we had heat flux that was perpendicular to the normal of the surface, then actually no heat would be flowing in. So we have to have the dot product there. Now, in this case, not always, but in this case, because we're saying the origin is the center of the hole, then the normal, it has to be the outward pointing normal of the domain, which means that it's pointing into the center of the hole. And so it's going to be minus x over r in the y direction, minus y over r in the j direction. And these minus signs weren't in the original version of the notes. That was a mistake. So make sure you correct that, or download a new copy of the notes. I'll post them. So the heat entering the boundary, Q bar, is going to be equal to Q star dot N. And so this is Q star again, dotted with N, which we just defined. I factored out the 1 over R. Actually, I think I factored it out twice, so let's get rid of that. And so what we're going to end up with is K over R squared times x squared plus y squared. And that, of course, just simplifies into being K. So it's very simple heat boundary condition. And so the plus sign here means that heat is flowing out of the domain. And that makes sense because if we look at the solution, then essentially we have the temperature is equal to R. So if this, for instance, was 1 and this is 2, I'm not worrying about the size of the plate here, but essentially as we go out, we're getting to larger temperatures. Heat must be flowing to lower temperatures, and so it's flowing out of the domain, so the sign is right. So yeah, the earlier version of the notes had an error there. Just make sure that you have that correct. And so that's basically it. Now, if the manufactured solution is any more complicated than this, or even in this case, a symbolic algebra package can give you a lot of help. I've demonstrated Mathematica earlier in the class. You can do this in MATLAB as well. This little bit of code is all you need. So this just says that I'm defining x, y, and k as symbolic variables. I define my temperature as the square root of x squared plus y squared. I define my heat flux as minus k times the gradient of temperature, and you have to specify what are the variables you're taking the gradient with respect to, so x and y. And then my heat force or heat flux is going to be, I want to simplify the expression of the divergence of the heat flux, or the divergence of the heat flux. And I think actually here we're actually missing a minus sign, which is why I had the mistake earlier on. So that's it for the method of manufactured solutions. With this, you can make any exact solution that you like, and then you just have to solve for, and it's relatively simple, you just have to take some derivatives, solve for the heat flux to which that solution is the exact solution. And the one last caution is that you have to choose the boundary conditions that are also consistent with that solution. So the simplest thing you can do is just apply the exact solution on the entire boundary. A little bit more complicated, but also a little bit more thorough as a check, is to specify the heat flux on the boundary, at least somewhere, so that you can test to see if your flux computation is correct. All right, that's it from now. We'll see you next week.